afternoon session in the number theory session. And it's a pleasure to me to announce Professor Victor Neumann from University of Uberlândia. And he's an expert in topics related to finite fields and number theory and so other topics. And today he will talk about existence of R primitive and Knormal elements in finite fields. Thanks a lot for accepting our invitation, Victor.
Thank you. Hello, everyone. It's very nice to me to be here in front of you. Before to begin to talk, I want to thank the organizers for the invitation on this event. And a special thanks to the organizers of this session, Professor Emar and Professor Mateus. We'll talk about existence of R primitive K-normal elements in finite fields. This is a joint work with Cicero Carvalho and Josimar Aguirre. We begin by defining this field, Fq to the n, the finite field of Q to the n elements, where Q is a prime power and n is a positive integer. This field has two main algebraic structures. Without zero is a cyclic group, and it is also a vector space over Fq of dimension n. In each of these structures, we have specific important elements. We say that an element alpha is primitive in Fq to the n if alpha generates this cyclic group. So it's the same thing as to say alpha has multiplicative order Q to the n minus 1. On the other structure, we say that alpha is normal if alpha and its conjugates form a basis of Fq to the n as a vector space of Fq. In this case, this basis is called a normal basis. Here we have a little example to understand how it works. We take Q equal to 2 and equal to 3. So this is the field of 8 elements. I take this element which this condition. So here we have the 8 elements. And we calculate, for example, the conjugates of a squared, a to the 4. And from the condition a to 3 to the 3 plus a cubed plus 1 plus a plus 1, multiplying by a, we get that a to the 4 is a squared plus a. So a plus a squared, these two conjugates, it's the sum of the first two conjugates, it's equal to the third. So the dimension given by this set is equal to 2. And so A is not normal. We also may see that every element which is different from 0 or 1 is primitive, because this cyclic group is of order 7. So every element which is not 1 is a generator of this cyclic group. And if we calculate the conjugate of a plus 1, we may see that they are linear independence, and so they generate the whole space. And so a plus 1 and a squared plus 1 and a squared plus a plus 1 are all of them normal elements of this field. So here I'm in red, so the normal elements, the blue, the not normal elements, all of them are primitive. So we have here, for example, 3 primitive normal elements. Okay, and These kind of elements are very important, primitive normal elements. And in fact, in 1987, Lenstra and Skov proved that we always have, for every prime power and every integer n, we always have a primitive normal basis of fq to the n over fq. The proof was given by steps. So first, Carl List in 52, he proved this result for q to the n sufficiently large. Davenport in 68 proved this for q prime. And finally, Lenstra and Skov proved this totally, completely. Okay. And Cohen and Husinska in 2003, they gives a proof free of computer. A well-known criterion for checking if an element is normal or not is this given by this theorem. So you take alpha and its conjugates. We put this as coefficient of a polynomial. So we take this polynomial. The coefficients of the polynomial are the conjugates of alpha. And if this polynomial and x to the n minus 1 are co-prime, then alpha is normal, or alpha and its conjugates form a normal basis. From this definition, or from this theorem, in 2013, Husinska, Millen, Panarion, Thompson defined the notion of Knormal elements. So we take the same polynomial as we see before, and they calculate the greatest common divisor of x to the n minus 1 and this polynomial. If it has degree k, we say that alpha is a k-normal element of fq to the n over fq. So, for example, if the degree is if they are co-prime, donc the greatest common divisor is 1, so of degree 0, then alpha is zero normal. So this is an extension of normal elements. So zero normal means normal, in fact. And they did some equivalence between different ways to define Knormal elements. For this, we need to define a linearized polynomial. So if we take any polynomial f and we substitute x to the I for x to the q to the I, we get the linearized polynomial of f. And with this definition, we may define the fq order of an element alpha of fq to the n. So a polynomial g is the fq order of alpha if g is the lowest degree monic polynomial, such that the linearized of g applied on alpha is 0. And in fact, we may prove that the set of polynomials which satisfies this equality is in fact an ideal of this ring of polynomials. Okay, so G is in fact the FQ order is the generator of this ideal. Okay, and if you take x to the n minus 1, the linearized polynomial of x to the n minus 1 is just, for example, x to the n is turned to x to the q to the n, and one is x to the 0, so it's turned to x to the 1. It means that if you substitute any alpha here, you have alpha to q to the n minus alpha, which is 0 for every element here. So it's for this reason that this element is in fact a multiple of G, or G is a divisor of x to the n minus 1. Well, this is the equivalence for K normality given by Husinska and others in 2013. We say so that alpha is K normal, which is given by this definition here, okay, from the greatest common divisor of x to the n minus 1 is G alpha. And the other way to see if an element is K normal is that the vector space generated by alpha and its conjugates is of dimension n minus k. Or we also may say that alpha is of FQ order. The FQ order of alpha is a polynomial of degree n minus k. So these three are equivalent. Obviously, the first one is the best in the sense of computer calculation. For the computer, I think it's best to just calculate a great common divisor. But we also have these other equivalents, which are important in theory. As we say before, zero normal is the same thing as normal. And Reyes in 2019 gives a method to construct Knormal elements. We may take beta, a normal element. F is a divisor of degree k. So the linearized of F at beta, it will be a K normal element. It is very interesting, and it is very easy to see that if we observe this exact sequence. In fact, the linearized polynomials are all of them linear maps of this vector space. So here we have exact sequence of linear maps and vector space. We prove this just by counting the zeros of each polynomials and by the fact that the composition of these two linear map is in fact the linearization of x to the n minus 1. So it sends 0 to 0. From this, we easily see this result here, this lemma. It's an m. So obviously, from this, LG de alpha equal to 0 means that alpha is on the kernel of this map, which is equal to the image of this other map. So there exists an alpha, there exists an beta, so that alpha is the linearized of F at beta. And conversely, also the same thing. And we also may see from this, we may prove, from this observation, we may prove also the observation of Lucas Reyes, which is that, we put that another way, an element. So if we take beta normal element, LF of beta is K normal. And conversely, in fact, we may prove that if an element is K normal, there exists an F and a beta, normal element beta, such that this happens. For this reason, we may say this another result. So there exist K normal elements if and only if there exist degree K factors of x to the n minus 1. Well, Husinska in this same paper present some open problems. The third of them, this is to determine the pairs nk such that there exists primitive k normal elements of fq to the n over fq. In this sense, Reyes and Thompson in 2018 proved the following results. They say that there always exist primitive one normal elements for n equal or greater or equal than 3, but for n equal to 2, there is no primitive one normal elements. So this is a general result, the complete result for k equal to 1. For the following results, we need a little definition. We denote W of m, the number of square-free divisors of m for a positive integer, and W of g, the number of square-free monic divisors of g for a monic polynomial. And Reyes, in 2019, proved that there exist primitive Knormal elements if this condition holds. But we need that x to the n minus 1 must have a divisor of degree k for the existence of Knormal elements. So this condition is fundamental, and this condition doesn't always happen. Okay, it is possible that it's not to be true, but exists primitive Knormal elements. The important here is that with this condition, we can prove that for sufficiently large Q, there always exist primitive Knormal elements, depending on this condition here of divisor of degree k. In this way, for k equal to 2 in 2021, we work in this case, and we prove that there exist primitive two normal elements if and only if n is greater or equal than 5 and q cube minus q and n are not co-prime, or if n is equal to 4, q must be congruent to 1 modulo 4. So we have here a complete result for the case of k equal to 2. Now, as we define k normal element which generalize normal elements, we can define R primitive elements which generalize primitive elements. So we say that an element alpha is R primitive if alpha has multiplicative order q to the n minus 1 over R. Obviously, R must be a divisor of q to the n minus 1. And so if we put R equal to 1, we observe that 1 primitivity is the same thing as primitivity. Another thing very important is that, in fact, alpha is an element R primitive if and only if it can be written as beta to the R for a primitive element beta. Okay. Well, with this definition, we may observe, we may go forward with the following problem, also proposed in the same work in 2013. Determine the existence of high-order k-normal elements alpha of fq to the n over fq, where high order means that alpha has multiplicative order n, where n is a large positive divisor of x to the n minus 1. In fact, say order of alpha equal to n means that R is equal to q to the n minus 1 over n. So in other words, the problem is determine the existence of R primitive K-normal elements for R small, okay? Because here high order R, high order n, high order n means small number r or r. Bon, our first finally result for some values is given by Kapetanakis and Reyes in 2019. We denote P, the characteristic of the field. So Q is a power of a prime P and a positive integer. And for P greater or equal than 3 and N greater or equal than 2, we always have two primitive normal elements, except in these two cases, when Q equal to 3 and N equal to 2 or 4. In fact, we need that P must be greater or equal than 3, because 2 primitivity means that 2 must be a divisor of Q to the N minus 1. So the characteristic of the field can't be 2. For this reason, is here P must be greater or equal than 3. So this means that this point solves completely the case of R equal to 2 and K equal to 0. And next, also for N greater or equal than 3, we always have two primitive, one normal elements. And for N equal to 2, there exists also this kind of element when Q is equal to 3, but not in the other cases. So this phrase, this result, solves completely the case also of K equal R equal to 2 and K equal to 1. So what we wanted to do is to have a general result about R primitive Knormal elements in the same way as it was given by Reyes for primitive Knormal elements. For this, we need some definitions to attack what we want to do. This definition is freeness, is a key in the work. So we take M, a divisor of Q to the N minus 1. We say that alpha is M free if for every divisor D of M, which is different from 1, there is not possible to write alpha as a beta to the G. There is no beta such that alpha is equal to beta to the G. And in the same way, we define G-free elements for polynomials, G a polynomial, in the same sense. So for every divisor H of G different from 1, it is not possible to write alpha as the image of some elements using the linearized of H. We also may see M-free and G-free using R primitive or the FQ order of a polynomial. In fact, if we take alpha, it must be R primitive for some R, some R, yes, because alpha must have an order. So say order of alpha equal to N. So R is equal to Q to the N minus 1 over N. And in this way, so take an alpha, this is R primitive for some R. And in fact, alpha will be M free if and only if R and M are coprime. And in the same way for G free, if alpha is an element of FQ order F, alpha will be G free if X to the minus 1 over F and G are coprime. In particular, we may state this result, because if alpha is primitive, R is 1. If R is 1, in fact, 1 is coprime to M for every M, in particular for N equal to Q to the N minus 1. So alpha primitive implies alpha Q to the N minus 1 free. And in the other sense, if alpha is Q to the N minus 1 free, so this must be equal to 1 for M equal to Q to the N minus 1. But R is a divisor of Q to the N minus 1. So the greatest common divisor of these two numbers is R. So R equal to 1, and so alpha is primitive. In the same way, we can prove this for normality. If alpha is normal, F is equal to x to the N minus 1, so it's equal to 1, and we may choose G to be x to the N minus 1. So alpha normal implies alpha x to the N minus 1 free. And if alpha is x to the N minus 1 free, so G is x to the N minus 1. This is a divisor of x to the N minus 1. So this GCG is equal to 1 and also equal to x to the N minus 1 over F. So F is equal to x to the N minus 1, which means that alpha is normal. Okay, so this result is very interesting to see the pictures of what means M free, what means G free. And this particular case is also very important to know how to write a primitive or normal element, because we have functions that can be calculated if an element is M free or G free, as we may see after that. So we define these characteristic functions. So this is the characteristic function of M free element. This is equal to 1 if alpha is M free, and 0 otherwise. And this is the characteristic function of G free elements. Okay, we define like that these functions, and we also need to define this other function with is equal to 1 if alpha is equal to 7. In the next page, we just show how to write these elements. For example, E0 of alpha must be written like that, where in fact here we denote like that the group of multiplicative character of this group. Okay, the group of multiplicative character is in fact the group of homomorphisms of this group to the complex number without 0. In the same way, we may prove that these two groups are isomorphic as the modules. And in the same way, we define the group of additive characters of Fq to the N. So this is an additive group. So the elements here are the maps of these additive groups to the complex multiplicatively, the group of multiplicative complex numbers. And we also may prove that these two are isomorphic as Fq to the Fq X modules. Okay. And so here we do the sum over all the additive characters on an element alpha, and this in fact it is equal to 0 except if alpha is 0. If alpha is 0, this is equal to 1, so this number here is equal to 1. So this is a way to calculate this using additive characters. We may do the same thing for these other characteristic functions. Okay, here I show you this. For example, the characteristic function of M3 elements must be written like that. Here, Euler is the Euler function, the Mobius function, and this sum is with this G in parentheses means that in fact we do the sum of all the multiplicative characters of order G. Okay, say every character here to the G is equal to 1, is not equal to 1 for every power less than G, for example. And here, for just it's a little complicated, but it is the same thing for the characteristic function of G-free elements. Here is also the Euler function for polynomials. Okay, so it's count the elements co-prime to F of degree less than F. Okay, and here the Mobius function also for polynomials. Okay, and this sum here is the sum over characters of FQ order H. I didn't define the order or FQ order of characters, but it's like it's defined by this isomorphism. So, for example, these two groups are isomorphic as Z modules. So we may define the order here by the order here. In the same way here for the FQ order of elements here and elements here. Well, I show you this just to give you a picture of how it can be written. Finally, in fact, the trick is this form. We denote like that this number, which depends on M and G. We do a sum over all elements of Fq to the n, beta and Fq to the n, alpha in Fq to the n without 0. Here, so the characteristic function of M-free elements, the characteristic function of G-free elements, and the characteristic function of 0. Okay, what this means? In fact, each of these elements in the product can be 0 or 1. So here I do the sum 1 plus 1 plus 1 plus 1 plus 0 plus 1, etc., etc. Now it counts only if each of them is 1. If one of them is 0, it doesn't count. But now what means so here? What counts this function? Well, to count a pair alpha beta, all of these must be 1. So this function counts the number of pairs alpha beta such that alpha is free, M free, beta is J free, and this is equal to 0. So alpha to the R equal to LF of beta. Okay. Well, now if you take M equal to x to the n minus 1 and G equal to x to the n minus 1, Q to the n minus 1 free means primitive. X to the n minus 1 free means normal. So this number here counts the number of the pairs alpha beta such that alpha is primitive, beta is normal, and alpha to the R is equal to L in F of beta. But now we need to remember that if alpha is primitive, alpha to the R is R primitive. If beta is normal, the linearized of F at beta is K normal because of the degree of F is equal to K. So if this number is greater than 0, this means that there exists at least one pair alpha beta such that alpha is primitive, beta is normal, and this is equal. It means that these elements it will be R primitive and K normal at the same time. So this is greater than 0 means the existence of R primitive K-normal elements. It is very important to observe that, in fact, it doesn't count the number of R primitive K-normal elements. This counts the pairs alpha beta such that this is R primitive and K-normal. So, in fact, as we fixed f of degree k, it is possible that there exist other polynomials of degree k which divides x to the n minus 1. So here we doesn't count maybe all the possibilities. And on the other side, you can have a lot of elements, alpha, beta, which gives the same element here. So it's very dangerous to say that we may count the number of R primitive K-normal elements. We can't do that. But we can say that if this is greater than 0, then there exists R primitive K-normal elements. And the proof now of how to evaluate this now, you may substitute this, and this with the formulas we give you here. We split this sum in values in some cases, okay, and we calculate some of them, and we bound some others, and we finally get this result here. So for Q a prime power and a positive integer, R divisor of x to the n minus 1, F a monic divisor of degree k, k must be of less than n over 2. If this happens, so this is the condition we get using these sums and splitting the sum in cases. So if this happens, so q to the n over 2 minus k greater or equal than this product, which depend on square free divisors of this number and polynomial. If this happens, then there exists an R primitive K-normal element of f to the n over fq. We may specialize this result by a technique used in a lot of works of the same kind. It's called the sieving technique. So we specialize that factoring x to the n minus 1 and factoring q to the n minus 1 and x to the n minus 1, these two. Okay, so the first part is as usual until here. We choose a divisor of q to the n minus 1. Here we put all the primes which divides q to the n minus 1 but are not divisor of L. We do the same thing for x to the n minus 1. We choose a polynomial g, and this is the set of all monic irreducible polynomials which divides x to the n minus 1 but are not factors of g. And we reorder these polynomials such that the first of them divides x to the n minus 1 over f. Okay, no, it is possible that s and s prime are equal, or maybe s prime is less than s. And we calculate this value delta. This is n minus this sum minus this another sum. And if this is greater than 0, so we must choose L and G such that the other primes, this sum must be greater than 0. If this is greater than 0, we define delta prime equal to this sum over over the polynomials which do not divide this. Okay, and we define delta, this sum here. We have delta and a number, delta prime another number, we do the sum, and the condition is here at the end. And if q to the n over 2 minus k is greater than r times delta times the number of free square divisors of L times the number of square free divisors of this polynomial, then this number will be greater than 0. In fact, this shift technique is very interesting because it's better than the previous one, this condition. So it is possible to take, for example, a q and an n, and it doesn't happen, but choosing well this divisor and this other divisor, it can be true, this inequality. So it's another way to, in case by case, to find if an element is R primitive and cannot. But we can specialize also this condition here by choosing L equal to q to the minus 1 and choosing g equal to 1 and doing some inequalities, and we get something like that, which is very general also. In fact, we need some conditions like q must be greater than n minus k to 2 square, and the other conditions are as usual. So if this happens, we have R primitive Knormal elements. Which is good here is that this is linear, okay? And normally when you substitute, when you do a substitution of this, you may do this as it's a power, okay? It's a power of 2. So here is a little better than that when n minus k squared is less or equal than q. With these results and doing some bounds of value of q to the minus 1, we may get this finally result. It seems to be a little complicated, but in fact, this one comes from the first condition, okay? This other one is the condition here, n minus k plus 2, in n minus k plus 2 is here, okay? And so if q is greater than this number, or if q is greater than this number, we have R primitive Knormal elements, okay? So we compare what is the minimum of this number and this number, and we choose that number to be the bound of q. But observe that here q must be greater than n minus k squared to take this bound here from the condition of the proposition before. Okay, so this is a numerical trick. The last one I will present you, and in fact after that we did a little example to show how it works, all these propositions. So this last proposition gives and t is just a real number greater than this one, which appear here in fact in this product. Okay, so you choose a number t such that you minimize this number here. It depends on n, on k, on r to know what choose to t. Well, now I did a little example. We take q a power of 11, and we study three primitives, three normal elements on these kind of fields. First, with the last inequality here, we take these conditions for the existence of three primitive, three normal elements. So for n sufficiently large, we get q greater than 11. But for n equal to 7, q is very, very, very large. Okay, we put here n greater or equal than 7 because we have the condition k less than n over 2. If n is equal to 6, okay, 3 would be equal to 6 over 2, and the result before doesn't work. So we put n greater or equal to 7. But for n equal to 7, this condition is, this number is very, very large. So we, in fact, for this specific case, we use the factorization of x to the 7 minus 1, and we get a more satisfactory bound here. Okay, and after that, we test these two conditions and this on all the pairs possible where q is a power of 11. There is not a lot of numbers. It's a finite set, and we use HMath to do that. And at the end, there are only 5 exceptions where for these numbers, this doesn't hold. So for these ones, we work explicitly as in the same, like in the first slide, where we take q equal to 2, n equal to 3, we calculate all the elements, etc., etc. So in fact, we calculate here some elements, and we try to find an element which is 3 normal and 3 primitive at the same time, and we succeed to find this kind of element. So the final result is what we say this in this proposition. For n greater or equal than 7, for q power of 11, if 3 divides q to the n minus 1, and if x to the n minus 1 has a factor of degree 3, then there always exist 3 primitive, 3 normal elements. And that is all what we want to show you. Thank you very much.
Thanks a lot, Victor. Let's thank the speaker, please. And now I will open for questions, remarks, and some comments.
I have a question. Victor,
Please,
you mentioned when you presented the result of Reyes 2019, you said that he has this bound on the size of the finite field, q to the some power bigger than something. And you mentioned that there was some examples that you can find normal and primitive with smaller finite fields, isn't it? You mentioned this.
In the first slides?
Yeah, when you presented the theorem of Reyes 2019.
This or another one?
No, Reyes.
Reyes.
And it's very similar to yours. There's a bound on K. Yes, this one. Is it this
Reyes. Reyes.
Yeah, Reyes. Yes.
Yes.
You mentioned that there are examples of fields with smaller cardinality, and still they have primitive K-normal elements.
Yes. Yes.
Yeah. Do you have the same for your theorem?
Okay. In fact, here, this condition, if this condition is true, there exist primitive Knormal elements. Mm-hmm. For example, when we did this theorem, we find some cases where this doesn't happen, but at hand, we find a primitive K-normal elements. Okay. Mm-hmm. On our result here, it is the same thing. Here, on our result is the same thing. For example, as I said here at the end, we test these two conditions. This always holds. Sometimes this condition doesn't hold, but this condition holds. But sometimes none of these condition holds. This is the case of these 5 examples.
Okay, I understand.
In these 5 cases, this doesn't hold, but we find 3 primitive, 3 normal elements.
A following question. I imagine that you have found also some examples of fields that does not have R primitive, K normal. Can you have an idea of a largest counterexample? How big this can be compared to your bounds?
Well,
this must be a very difficult question, but
in fact, if Q is greater than this number, there always have R primitive K normal elements. K normal, where K must be less than N over 2. Okay, so if with this condition in mind, we don't know if, in fact, for the moment, I think there is not example of field with non-R primitive K normal elements. In fact, when Husinska and others propose this problem here, they doesn't know if there is not possible to find this kind of element, because for Q sufficiently large, there always exists R primitive K normal, but R and K are they can be anything. So, for example, Kapetanakis and Reyes, the others, they begin to work with very small numbers. They find some exceptions with this very small. In the case of for example, where in the case of in the case of R equal to 1 and K equal to 2, there is no exception, because these two conditions, in fact, is the condition for the existence of K normal elements. And just for the case where N equal to 4, we must prove just algebraically that if Q is not congruent to 1 modulo 4, there is no element primitive to normal. But if Q is congruent to 1 modulo 4, we can do some tricks to find some conditions like that for this special case, and for the other case, we may do our work hand by hand also. So it's very difficult. You take R equal to 2, N equal to 2. We must study what happens in this case, because at the moment no one's work with R primitive K normal. The first step is to find this here. The first step is to find this condition. Now we have this condition, we may work for specific R and K, see what happens. The problem is that for Q and N very large, it's very difficult to calculate if there is R primitive K normal elements, even with a computer. On our cases, for example, we began with these two conditions after did this bound first, and when by lucky, the only exception was numbers not so big. So if you take K larger or R larger, the numbers, the exceptions may be very large, and in this case, it will be very difficult to calculate.
Yes, I understand. Okay, thank you very much.
Are there other questions? Let me ask you something, Victor. Emar did a really good question. And by thinking on future works and future directions, do you think that it could be of interest to see which conditions we must put on these parameters so we don't have these R primitive, Knormal, and so on? Because it seems that all theorems you put some conditions and you ensure that there is this primitive element with normal over the field. And I was wondering if we could provide some families of parameters such that there is not primitive element and R primitive and Knormal element. What do you think about it? Do you have a guess?
I don't have a guess, but if it will be possible, it will be very interesting, because here we have some conditions. So R must be a divisor of q to the n minus 1, k must be less than n over 2, there must exist a degree k factor of x to the n minus 1. With these conditions, I think it will be very difficult to find families of q and n with no R and k, R primitive and k normal element. But if someone did that, I think it will be very interesting, because it's the opposite direction of thinking that there always exist R primitive k normal elements. If k is less than n over 2, maybe if R is less than square root of q, for example, I don't know. But there is these two directions. These two directions are there exist elements or fields where doesn't happen, or if the conditions of existence of R primitive elements and k normal elements, we always have the two combined. All of them are conjectures, opposite conjectures. In proof R primitive k normal, I think is very difficult with with what we have in hand now, because all what you have is conditions like that, and after that you must do hand by hand, at hand, every case, and you don't have some structural property. It will be very interesting if you find, for example, some structural property on or in the other side, if you provide this kind of examples, as you say. I don't know if it is possible. My guess is that we always have R primitive k normal element. That's my guess. Is for that I think very, very difficult to find a family of pairs where it doesn't happen.
Perfect, Victor. Thanks a lot. Thank you for your nice talk. So let's thank Victor again, please.